All right, good afternoon or whenever you're watching this to everybody. Here are the notes for uh, rectilinear motion, or basically motion along a straight line. And so what we're going to talk about is two scenarios. If we have x of t, we're talking about a particle that moves either right or maybe left or bounces, but it stays along a horizontal line. Okay, so it's only going to move right or left. If we have a function defined in terms of y of t, then it's the same scenario. The particle is going to move only up or down. So we have like a vertical axis. Okay, and so just like with regular motion, we still have velocity is going to be the derivative of the position function. Okay, or you could also say velocity will be the derivative of y of t, depending on which direction things are moving here. Acceleration is still the first derivative of velocity or the second derivative of position. Okay, and this one we haven't talked about too much, but right here, okay, speed is the absolute value of velocity. And the reason for that, okay, and I give you an example, like let's say you're driving in your car. Your car gives you a speed of travel, right? 45 miles per hour. That's a speed. It doesn't matter what direction you're going. You could be going north, east, south, west. Doesn't matter. It's 45 miles per hour. Now, if we attach directions, now we have velocity. Okay, and this gets into dealing with vectors, but we're not going to talk about that. A velocity has a magnitude or a value, 45 miles per hour, and it also has a direction to the right, to the left, up, down, east, west, north, or south. Okay, but if all we're interested in is how fast something is moving, that's speed. So in math, okay, when we have negative signs for velocity, that indicates opposite direction, right? And so basically what you need to know is that for a horizontal axis, right means positive in general, left is going to be negative, okay? So if our position is 5, that means we're 5 units to the right of where we started. Okay? If our position is negative 5, that means we're 5 units to the left. Okay? If our velocity is positive, that means we're moving right. If our velocity is negative, that means we're moving left. Okay? Acceleration, that means we're speeding up this direction, right? So we're increasing our velocity to the right. Here we're decreasing our velocity to the left. Okay? And so for these types of problems, and obviously similarly with y, right? Except now we have, for y of t, up is positive, down is negative. Okay? So just as long as you can remember that, you guys should be in good shape. All right, so now what are we going to do with all this? Well, we're going to try to describe the motion in detail, like what's happening, what's going on, where is it moving, is it slowing down, is it speeding up, that kind of thing. And so these are the bits of information when it says to describe the motion. These are all the different things that you should be able to do. Okay? And so times when the particle stops moving, that's simply when the velocity is equal to 0. Okay? And again, I'm doing these assuming that we're talking about horizontal movement. Okay? So the same still applies if we're talking vertical for y of t, except instead of left and right, we're going to use down and up. Okay? Anyway, so if a particle stops moving, so let's say we're moving to the right, but then we stop suddenly, that's when the velocity is 0. Okay? Intervals when the particle is actually moving left or moving right. So moving means that velocity is going to be less than 0. If the velocity is positive, that means we're moving right. All right, accelerating and decelerating. Okay, so easiest way to think about this is, let's say you're driving in a car, right? So if you're driving this way and you start speeding up, you're going to keep moving the same direction and cover more ground. In other words, you're moving this way, so your velocity is going this way, and your acceleration is also pointing in the same direction. Okay? That's like you pressing on the accelerator. Now, if you're decelerating, so you're traveling this way, but you step on the brakes, well, then you slow down, but you're still moving the same way. So in other words, now you're kind of being pulled the other way. That's what's slowing you down. And so we get opposite directions. Okay, and that's actually what, and again, I'm trying not to get into too much of the physics or talk about vectors here, but basically what you need to know, okay, is in order for things to be accelerating or speeding up, that velocity and acceleration are in the same direction. In other words, the velocity is greater than 0, acceleration is greater than 0, or the other scenario is we're moving left and we're accelerating left. Okay? Decelerating, that's going to be when velocity and acceleration are opposite directions. Okay? So that means velocity is greater than 0, so that means we're moving to the right, but now acceleration is negative. So that's the example I gave over here where we're moving to the right, but then we're braking, right? That would be the scenario right here. And the other case is moving left, so velocity is negative, but now acceleration is positive. Okay, so if you can remember, accelerating, same sign, positive, positive, negative, negative, you're good. Decelerating, opposite signs. Okay. Displacement is overall change in position. Okay. And so that's simply found by plugging in values into x of t, into your position function. So if this is our interval, we start at A, we end at B, then all you would do is subtract x of B minus x of A. Okay, pretty simple. Average velocity, well, it's similar to what we did before, right? So previously, we did S of B minus S of A over B minus A. And I should add average velocity of the particle on the interval from A to B. Okay. Previously, we just did average rate of change formula, or slope, whatever you want to call it, S of B minus S of A over B minus A. The only thing that changes now is if we're doing X for position, that we use X. So it's actually no different. So you do X of B minus X of A over B minus A. Average rate of change is the same as average velocity, synonymous with slope. Okay, so these are all the details that we needed to cover as far as how to answer the question. So now we're going to go ahead and go on to the first example. We're going to try to answer all these questions to describe the motion. Okay, so let's go ahead and again, I'm going to try to just, I'm going to follow A, B, C, D, and E as described previously. Okay. So first, Part A. Okay. To describe the motion, we're going to talk about times when the particle stops moving, right? So to find that, we find the velocity. We know velocity is just the first derivative of position. So looking at our position function, we take the derivative. So that's going to be 3t squared minus 24t plus 36. Now we set that equal to 0, right? Because we want to know when the velocity is going to equal 0. Probably easy to factor out a 3 first. So you get t squared minus 8t plus 12. You can continue factoring. T minus 4, or sorry, t minus 6, I should say. T minus 6 and t minus 2. And so that means if we set each of these equal to 0, that t equals 6 and t equals 2. So the particle is stopped. It's not moving when t equals 6 and t equals 2. Okay? Part B. When is this moving left? When is it moving right? Okay, so let's take a look at our interval. We're going from -1 to 9. And these values that we have up here, these are the same values that we would get when we do critical numbers, right? Because we set the derivative equal to 0. We found two values. So that's exactly what we do to find critical numbers. And so we're going to do a sign chart because we want to know when the velocity, right? When is the velocity positive? When is the velocity negative? Because that'll tell us moving left and moving right. All right, so if we test a couple of values, here we can test 0. Here maybe I'll test 3. Here I can test 7. And remember, we're plugging these values into here, right? So if you plug in 0, you're going to get a negative times a negative, which is positive. If you plug in 3, a negative times a positive, that's negative. If you plug in 7, both of those will be positive. And so now we can say that the particle moves left on the interval from 2 to 6, and that's because the velocity, or x prime, is negative. Okay? And the other two intervals, we're moving right. So the particle moves right on the interval from -1 to 2, and we're going to combine that with, so union, interval from 6 to 9. And again, that's because the velocity there is positive. Remember, x prime is velocity. Okay? All right. So what do we discuss next? Accelerating and decelerating. Let's get to that. So now what we want to do is find the second derivative. Find acceleration, right? Acceleration is going to be the second derivative. And since we have the first derivative up here, now we're going to just take the derivative a second time. And so we're going to get 6t minus 24. Set that equal to 0. You're going to get t equals 4. And now what we want to do is kind of compare, right? We want to look at the velocity and the acceleration. So I like to kind of compare everything. So let me copy down. So this is x prime right here. -1, 9. So this is velocity, right? Acceleration, same number line. Okay, so we're going to compare what's going on. We've already established that we have critical numbers of 2 and 6 for velocity. Here we have positive, negative, positive. I'm going to copy those numbers down below into the acceleration sign chart. But I'm also going to insert t equals 4 in here now, right? And now we're going to test some values. So here again, I'll test 0. Maybe I'll test 3 here, test 5, test 7. And we're going to plug this in to acceleration. Okay? If I plug 0 in, that's negative. If you plug 3 in, 18 minus 24, that's negative. Plug in 5, now we're positive. Plug in 7, now we're positive again. Okay, so now we can kind of compare. Okay? So what's happening here? Remember that acceleration happens when velocity and acceleration are the same direction, or both positive or both negative. So that happens a couple of times. Right here, from negative 2 to 4, you can see that we have negative above and negative here. So these are the two, that's one time when it's accelerating right here. And then right here from 6 to 9, we got both positive. Okay? So we're going to say accelerating on the intervals from 2 to 4, 6 to 9, since velocity and acceleration have the same sign. And now let's do decelerating. So for decelerating, we want opposite signs. And you can see that from negative 1 to 2, we have velocity positive, acceleration negative. So right here, okay, we have opposite signs. And also from 4 to 6, we have positive acceleration, but right here we have a negative velocity. So we're going to decelerate on the intervals from negative 1 to 2 and 4 to 6. And that's since the velocity and acceleration, ooh, looks like this marker is on its way out, have opposite signs. Okay? Moving on to the fourth thing. What is part D? Displacement. Displacement. So overall displacement, all we do is we start at negative 1 for time and we end at 9. We plug those both into the position function and we subtract. So we do x of 9 minus x of 1. Okay, and so if you plug in 9 into the, I'm going to save the time here. You plug that in, evaluate it, you're going to get 61. Okay, we're going to subtract, plug in 1. Okay, you're going to get negative 69. And so you're going to be 130. You're going to be 130. What units are we in? Centimeters here. And this is to the right of where we started. Okay, so whatever the starting position was, we have moved 130 centimeters to the right. And now for part E, average velocity. Okay, so now we just do our average rate of change formula, which is x of 9 minus x of 1 over 9 minus 1. We've actually, in the previous part, already calculated x of 9 minus x of 1. That's 130 centimeters divided by 8. And that's going to be, going a little too quick. 9 minus, these were negative ones. I am so sorry about that. Our initial position started at negative 1, and then we went to 9. So when we do the displacement, it's final time value plugged in, and then you subtract whatever you get when you plug in the initial time value, which is negative 1. These answers are correct. I don't know why I omitted that. And so down here, this will be 9 minus negative 1, which turns into 10. And so that gives us 13, and this is centimeters per second. All right, so that's all the details when we talk about describing the motion. Okay, that's kind of what we mean there. Come on. All right, just making sure we're still recording. Computer went in standby mode. All right, so the last thing is now answering some of these questions with a calculator. All right, so if they give you, here's a word of advice. If they give you a graph grid and they actually have like everything labeled, that's the first thing I'm going to do. I'm going to change my window. So if you go to window, right, you're going to change the window to match what you see here. We're going from 0 to 6 on the x-axis. We're going from -4 to +4 on the y-axis. And it looks like we're counting by ones, both directions. So my x scale and y scale should stay at 1. Next, you're going to type in the function. Okay, so now remember that this is the velocity. Okay, and so if you type that in, even though we don't use t, just remember that when you type in the variable button right here, that x really is time in this graph. And if you go ahead and make sure we're in radians, right? For calc, we're always in radians. Go ahead and graph. You get something that looks like this. All right. So if you try to just kind of copy that a little bit, it looks like we have a point that starts right around there. Around 1, it goes through. It looks like we reach a low point near 3, not quite at 3, almost at 3, so maybe like right about, or almost at -3, so something like that. And then 1, 2, 3, 4, almost at 5, we hit the x-axis again. Then we kind of level off around here. So okay, so I'm just going to kind of, so something like that maybe. Okay. And now let's go ahead and answer some questions. So over what intervals is the particle moving down the axis? So we're talking about a vertical axis. We're talking about either moving down or moving up, right? And basically moving down means the velocity has to be negative. Okay, well, that is going to happen when the velocity graph is below 0. So basically from here to here. So easiest way to do that on the calculator, if you find the zeros, so you can figure out what those x-intercepts are. Again, you go second, calc, go to 0, go to the left of the first x-intercept, go to the right of the intercept, you get about 1.016. And then for this one, same thing, go to the left of it. It's probably faster to just type in the value, but for those of you that are visual, this might be easier. Here we get 4.68. Let's go 1. Or I guess we could just truncate it, right? As long as we're accurate to 3 decimals, we can just make it 4.68. Okay. Either round or just remove everything after the third decimal place, so third decimal place, so 4.68 is fine. All right, so we have enough to answer this question, right? So between 1.016 and 4.68, so this is on the interval 1.016 to 4.68, and that is because the velocity is negative there. Okay? All right, next question. At t equals 4, is the particle speeding up or slowing down? Okay, speeding up means accelerating. Slowing down means decelerating. So let's take a look. At 4, looks like the velocity is below 0. So velocity at 4 is less than 0. The acceleration, which is the slope of the velocity, okay? You can see right here that at 4, my acceleration, which is the slope of the tangent line here, is positive. Okay? So this means that we are slowing down. Since the velocity and acceleration have opposite signs. All right. And finally, oh, and I should also mention, you could also like plug in the values. So if you actually go back to a table, you look at 4, okay, the velocity is going to be negative 1.35. The acceleration, okay, I'm not going to do that now because I don't want to make this video too long. Remember that what you can do is go to math. Actually, I might as well talk about it real quick. And then do the derivative feature. Go to y-vars. All right, and then what you can do is get now y1 is your velocity values at 4, and then y2 is your acceleration values at 4. So you can see right there if you do it graphically on the calculator. So on the calculator, you get negative for velocity, positive for acceleration. If you just look at the graph, you could just say, well, the tangent line slope here, clearly it's positive. So that means acceleration is positive. And obviously, we know that the velocity here is negative because the velocity function is below 0. Okay, so a couple ways that you can justify that. But the important thing is the conclusion. You have to state that the velocity and acceleration have opposite signs. All right, fastest speed. Fastest speed. Remember that this is just the absolute value of the velocity. So probably the fastest way to do it, if you think about the velocity graph, we just need to make everything positive. So here we're positive, that's good. So this is going to, the speed and the velocity are one and the same. But right here, when the velocity becomes negative, what we can do is kind of flip this part over. So it kind of mirrors. So this green part mirrors what's going on down here. And it's pretty clear that up here, this would be the max. Okay? And so what you could do now is on the calculator, I'm actually going to find the minimum because it's going to correspond to this point. Whoop. Don't need to graph my derivative now. If you find the minimum, okay, because this point is the one that's furthest away from 0. Actually, that would be another way to describe the fastest speed. Whatever point is furthest away from 0, which is going to happen here, you take the absolute value of the y coordinate there. So we find the minimum, go left bound, go right bound. So right here, the minimum is negative 2.780. So that means that positive 2.78 is going to be, sorry about that, so 2.780, that'll be the fastest speed because that's the farthest we get from the x-axis. All right. Hopefully that takes care of that. And this is the end of stuff that is on your final exam.